Hey folks, it's Mr. Ray here with our next lesson in grade 11 University Math. We're working in the unit on functions and transformations. We are now, we have the basic background knowledge of what functions are, what domain and range are, what function notation is. So what we're going to do now is the next, I believe it's 4, maybe 5 lessons are all about being able to create different families of functions and being able to graph any of those types of functions. So today's lesson is the starting point for that. It's called base functions. So we're going to be looking at 5 base functions, which is basically, you could call it a parent function that you could apply all sorts of transformations to create a whole family of that type of function. So we're going to look at each of the base functions separately. We're going to look at what the graph looks like of the base function, what the equation is. We're going to look at any special features such as whether they're symmetrical or not, the domain and range, and the key base points. Now the key base points are going to be important once we get into our graphing, because we're going to start with those base points and transform them to create the new graph. So let's just read through the definition. Base function, I think I've covered some of it. Every function can be categorized into a particular family of functions. Each family of functions has a base or parent function from which all other family member functions can be created using transformations. Some of the most common base functions are linear, quadratic, square root, absolute value, and reciprocal. So those are the 5 base functions we're going to look at. So if we start with the first base function, this is something you probably spent all of grade 9 or most of grade 9 math looking at. Linear functions. Of course, you didn't call it a function back then. It was a linear relation. But now that we know it's what functions are, we're going to bump that up into the category of linear functions. So we're also going to apply the function notation. So the equation of our base linear function is just f of x equals x. In other words, what we used to call y equals x. So here's the graph of y equals x. This is the parent function of all other linear functions. So the graph, you can see it's a straight line. It does continue at both ends forever. It passes to the origin 0, 0. So let's talk about some of the things we're going to talk about here. So the domain, basically the domain of almost all linear functions is all real numbers. In fact, for the purpose of grade 11, we can say all linear functions have the domain of this, all real numbers. And unless the line happens to be horizontal, which is a linear function, this base function and 99% of all other linear functions have the range. Now that we're using function notation, I could actually define the range as f of x. Instead of using y now, we could say f of x is an element of the real numbers. I'll put in brackets y is an element of r. I would accept this, the y, but as we move into more advanced math, we should try to avoid using y if the function itself is f of x or g of x or whatever it happens to be. So we should use whatever function notation is on the left side to define what the range is. Okay, so that's the domain range. Special features and symmetry. Well, it's not symmetrical. I can't do a mirror image from top to bottom or from left to right. And there's really nothing to speak of for linear functions in terms of special features, so we'll just say none. Okay, now here are the key base points. These are things that once we get into future lessons, you will basically write this, well, depending on which base function you're dealing with, you will be writing this set of base points to start with all the time. So this is something you should get used to and memorize. Fortunately, a lot of the base functions have very similar looking base points, at least for the x values anyways. So for the linear function, we're going to just basically define basically what the base points are going to do is we're going to provide enough base points that if I was to plot them, it would give me a really good representation of what that function looks like. Now for a line, all you really need is 2 points. But in order to be consistent with some of the other functions, I'm going to give probably more than we have to. So we're actually going to put the x values from -2, increasing by 1 until we get to 2. So from -2 to +2. And if you calculate what the y coordinate is, or f of x, it's just f of x equals x. So the f of x, or the y value, is going to be the same as the x value all the time. And this is just the base function. So there's our base points for a linear function. Okay, so let's move on to our next base function. And this should be very familiar from grade 10. Second base function is the quadratic function. So our base equation is f of x equals x squared, and that is basically the parent quadratic function of all other quadratic functions. So this is what the graph looks like if you were to graph that using technology or by hand. Now in terms of, I put the arrows on because it does continue forever in both directions. Special features and symmetry. Well, we know that the graph of a quadratic function is a parabola, and parabolas are symmetrical. So it definitely has some symmetry. And another special feature that parabolas have is the vertex. So the vertex of the base function, f of x equals x, the vertex is the point 0, 0. So that's important. And we can also say it's got symmetry, and it's symmetry basically about the y-axis. So if I put a line down the middle, basically where the y-axis is, you can see that would be a reflection, left-right reflection. We can say it's symmetry about, you could either say the y-axis or about the line x equals 0, which is the y-axis. The domain and range. If you remember, the domain of any quadratic function, including this one, is basically all real numbers, because your graph will extend in both directions, left and right, forever. There's no restriction on the x value. Now there is a restriction on the y coordinate, or f of x, because of the vertex. All the points are either above or below that. So for this base function, y equals x squared, f of x equals x squared, we would say the range is f of x is a real number. And again, you could put y if you're struggling with this. And for this example, y could be 0. It can't be anything negative, but it could be 0 or anything above. So f of x is greater than or equal to 0. That's our restriction. That's basically saying the y coordinate can't be negative. Okay, now in terms of the base points, again, we want to give enough points that if I just gave you the points, you could do a good representation of what that graph looks like. So we have our x and our f of x equals x squared. And again, just like the linear base function, we are going to do the same x values, -2 up to +2. And the reason why we're choosing these, we really have to have the vertex there. That's a key point for graphing. So we've got the 0 there, and in order to get the shape nice, whether it's going up or down, or how narrow or how wide it is, having 2 points to the left and 2 points to the right of the vertex will give us a good idea of what that graph looks like. So that's why we chose those 5 points. And when we square these values, don't forget, when you square a negative number, it's positive. So we get negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, and 1 squared is 1, 2 squared is 4. You can see these points, there's some symmetry about there, and that's because the graph is symmetrical, which we just talked about. Okay, so those 2 functions should be very familiar. Linear and quadratic is what we spent most of grade 9 and 10 looking at. So the next 3 are maybe not brand new, but we haven't really worked a lot with them in high school math. So the next base function is the square root function. So I'm not sure why this looks like it's sunk here, but it's just f of x equals square root of x. Now this graph here, just to make sure it's clear, that point at the origin is at 0, 0, and the line goes only in this direction, and it keeps going forever like that. Okay, basically this is like a parabola on its side, but only 1/2 of it. Okay, now in terms of the special features, well, this is the first graph we've had where we actually had an endpoint. All the other graphs so far are basically headed in both directions forever and ever. So we're going to say that 0, 0 is an endpoint, meaning it stops there. Okay, domain and range. So you can see here, if I was looking at what are the possible x values for this base function, f of x equals square root of x, you can see x can start at 0, and anything greater than 0 or equal to 0. It can't be anything less than 0. We didn't even show the graph for that because this function does not, you can't, the reason why it doesn't go past here is you can't take the square root of a negative number. You can't take the square root of 0. You can't take the square root of anything positive. So that's why the graph looks like this and why it doesn't extend beyond the left of the origin. So in terms of the domain, we can say that x is an element of the real numbers, but this time x has to be greater than or equal to 0, because 0, 0 is an endpoint, which we just talked about. Now for the range, f of x, which is also known as y, y is an element of the real numbers. Now in terms of what the possible values of y are, it's very similar to what x was, because y can go as low as 0, it can't be negative, and anything above 0 is going to be a point that this graph will eventually hit. So exactly the same, except this time it's f of x is greater than or equal to 0. Okay, now in terms of the base points, and again this is going to be important later on, we have our x and we have our f of x equals square root of x. Okay, so these are going to be different than the previous tables, really just because we can't have any negative values here, but also we want to pick values that will give us integer coordinates. So for example, I'm definitely going to have 0, 0 here, square root of 0, 0. That's an important point because that's where the graph of the function starts. And I'm going to have x equals 1, I can take the square root of 1, that's also 1. But if I put x equals 2 here, took the square root of it, that's a decimal that never ends. So I'm going to skip that. I'm also going to skip 3 because I get the same issue. So I'm basically going to pick some perfect square numbers for my x values. So square root of 4 is 2, that gives a nice integer. And you can see how this is going. the next number I'm going to pick is 9, because that gives the square root of 9 is 3. So I'm going to use those 4 points as our base points for this family of functions. So anytime I have something like that, I'm going to start off with these base points because, well, they give a nice, if I was to plot them, they'd give a nice shape of what the graph looks like, but it also gives integer only values, so it's a lot easier for graphing and for working with later on. Okay, so that's base function number 3. 2 more to do. This one here, I have no idea why it's showing up like this. This looks like it's like an X with 2 bars to the left and the right. Okay, and this function, when you see those 2 lines, that's called the absolute value function. So it hasn't been talked about too much in math up till now, but what the absolute value function does, it's a very simple thing. If the number is negative, it just strips off the negative sign. If the number is positive, it doesn't change it at all. So for example, the absolute value of 3 is 3. Absolute value of negative 3 is positive 3. Okay, so if you were to graph that, so for example, if you looked at the right branch here, I'll put my arrows here so I don't forget. The left branch is just, it's like the line y equals x, because whatever x is, if x is 4, well, f of x is also 4, because absolute value doesn't change the value if x is positive. But if it's negative, you can see this line kind of looks like a V at that point, because if I take the absolute value of negative 1, the result is positive 1. If I take the absolute value of negative 5, the result is positive 5. So that's what the absolute value function does. You won't see it a whole lot, but it will be used as one of these 5 base functions in grade 11. Okay, let's talk about some of the features. Well, this time, same as a parabola, this just looks like a jagged, very straight parabola almost. If you put a line down the middle, it is symmetrical about x equals 0, just like f of x equals x squared is. So we can say there's symmetry, and it's symmetrical about x equals 0. That means on both sides of that line, the graph and the function is symmetrical. X equals 0 is just another way of saying the y-axis. Okay, in terms of the domain and range, very similar to what the second base function, the quadratic function. You can see that the x values can be anything. So for the domain, we're going to say that x is an element of the real numbers, no restrictions. And for the range, just like the quadratic, it can only be above this origin here. It can't be negative. So in terms of the range, we've got f of x is an element of the real numbers, and f of x has to be greater than or equal to 0. And like I said before, if you're still not comfortable with f of x, you could put y here, and I'm okay with that for grade 11. Not so much for grade 12. Okay, so you get an idea of what this function does, some of the properties, domain, range. Let's talk about some the key base points that we're going to use, and we're going to be try to stick to the same base points that we use for quadratic. Just because obviously we need that 0, 0 point, because that's where the line changes, where the function changes direction, and we're going to pick 2 points to the left, 2 points to the right. So let me write this here. So we're going to pick the same x values as we did for linear and quadratic. So that is -2 up to +2. Okay, and now when you actually apply the function to these x values, like I said, it's only affecting the negative values. So 0, 1, and 2 don't change because they're not negative, but the negative values here change to positive values. So you have 2, 1, 0, 1, 2 as your y coordinates or your f of x values. Okay, so that's the absolute value function. I know it's brand new, so might take a bit getting used to. This next function is probably the most complicated of all 5. It's called the reciprocal function, and it's written as f of x equals 1 over x. So what this function does is whatever your x value is, it flips it. So for example, if your x value is 2, your f of x or y value is 1/2. So let's zoom in on this a little bit just so you get a better idea. So you can actually see this is a strange looking graph because it's got 2 parts to it. We call these branches, a left branch and a right branch. Both of these branches go off forever in both directions. So this time you actually have 4 arrows because you have 2 branches. Now if you look at what's going on here, like what I talked about, if x is 1, then your y coordinate is going to be 1. So 1 over 1 is 1. If your x value was 2, then your y coordinate is 1 over 2, 1/2. X value is 3, y value is 1/3, 1/4, 1/5, 1/6, 1/7. It keeps going. Now the interesting thing about this, if I keep going here, it looks like it's going to cross 0, y equals 0, but it doesn't, because as big as x gets, the y value will just be 1 over that value. So if x is 1,000,000, the y coordinate is 1/1,000,000th. It's still positive, it's still above, but it's never going to get to 0. Now we call this line here, the x-axis and the y-axis, which we'll talk about in a second. We call this x-axis an asymptote. An asymptote is a line. It's not part of the actual graph of the function, but it's important because it's a line that the function will approach but never quite get there. It never gets there. So, and the same thing happens over here on the left. If my x value is -1, my y value is -1, 1 over -1, 1 over -2, 1 over -3. So it's -1/4, -1/5, -6, -7, all the way up, like -1/1,000,000th. It's still below 0, but very, very close to 0. So this x-axis is an asymptote because we can never actually have a y value of 0. Okay, and another way of looking at that is you could look at the function itself and say, well, the function is 1 over x. Can I ever have a value of 0 here? Well, the only way I can have a value of 0 here is if the top is 0. Okay, and the top obviously can never be 0 because it's always 1. So that's another clue that f of x or y can never be 0. Okay, now the other aspect of this is the y-axis. Okay, you can see this graph zooms up really close to it and zooms down really close to it. Now what happens on this side, if I have an x value that's a fraction, so if x is 1/2, f of x is 1 over 1/2, which is 1 divided by half, which is 2. So if x is 1/2, y is 2. If x is 1/3, y is 3. So basically it's kind of doing the opposite of what it was doing this end. It's getting really, really big fast. So for example, if I picked a really small value, let's go with 100. If x is 1/100th, okay, really close to here, then my y value is 1 over 100th, which is actually equal to 100. So this is it's taking off really fast, getting more and more positive as we get closer and closer to 0. Now what happens at 0, if x is 0, well, the function f of x says it's 1 over 0. Well, that violates the most precious math rule about dividing by 0. There's no value for the function at x equals 0. So because of that, the y-axis is also an asymptote. So this is a very peculiar function. You've got 2 asymptotes. which causes you to have two branches. Okay, so that might be your first look at this function, but it's going to be used a fair bit in grade 11 and 12. So you can't avoid this one. It's going to be there quite a bit. Now, like I said, we have two asymptotes. Now, we actually can qualify an asymptote as either vertical, if it's a straight line, you have a vertical asymptote, or it's a horizontal asymptote, if it's a horizontal line. So in this case, we have a vertical asymptote. And here's how you spell asymptote, A-S-Y-M-P-T-O-T-E. And that's at x equals 0, or the y-axis. And you also have a horizontal asymptote. And that's at y equals 0. Now, normally when we graph this, and I'll be showing you this later, I kind of penciled this in there, but if you're showing asymptotes usually, what we usually do is like a dashed line. And it's hard to do a dashed line on the x and y axis because you've already got a solid line, but that's kind of our goal, is to show asymptotes as dashed lines. Okay, now if we go to the domain of the reciprocal function, start off by saying x can be any real number. Now for this one, there's only one value of x that this function can't have, and that's x equals 0. So it's a lot easier to say what the domain can't be instead of what it can be. So what we're going to say here is, instead of saying x has to be less than 0 and x has to be greater than 0, we're just going to say x cannot be 0. It's a lot easier to think of it that way than to say what it can be. And the range is exactly the same. We start off by saying f of x is an element of the real numbers, but f of x or y cannot be 0. So the only values that this function can ever have is x being 0 or y being 0. Okay, so that's it's an important new function. I know it's a little different than all the other ones we've done, more complicated looking, lots of different features and symmetry going on. Now this does have symmetry, but it's not the same type of symmetry that we've seen with the other functions, where it's a mirror to the left and right or to the top and bottom. So we're going to learn about this type of symmetry in grade 12, but for the time now, we'll just say that it doesn't have symmetry, but it sort of does, but not the type that we're used to. Okay, now in terms of base points, this is where this function gets interesting. So we got f, and f of x equals 1 over x as our coordinates. Now, what I can't do is, I definitely can't put x equals 0 for this, because then I would get an undefined point or a non-existent point. So I need points that I can actually graph for this. So what I'm going to do, I'm going to start halfway down here. So I'm going to pick, I can't pick 0, so I'll pick a point that's close to 0, but still positive. So I'm going to start with 0.5 or 1/2, and I'm also going to pick 1, and I'm also going to pick 2. And then, so what that does is it gives me 3 points. It gives me this point here, which is kind of like in the middle of this curve, and it's going to give me another point over here, which shows it's going up, and then this third point over here, which shows it's going towards the x-axis. So those 3 points will give me a good idea how to graph that, and I'll do exactly the same for the left side. So I'll pick the same 3 points, but this time negative. So I'll try to keep these sequential or ascending. So negative 0.5, negative 1, negative 2. Okay, so got an extra point here because of how this is more complicated, how we have 2 branches, also how we can't have 0 as a point. So if I plug in these x values into the 1 over x, and I'll keep these as decimals. So 1 over negative 2, well, that would be negative 0.5 or negative 1/2. Negative 1, so 1 over negative 1, that's just negative 1. 1 over negative 0.5, well, that actually works out to negative 2. Okay, and I almost feel like I should break this these base points into two groups, because these 3 points will be the points for the left branch. These 3 points will be the points for the right branch. So 0.5 or 1/2. 1 over 0.5 is positive 2. 1 over 1 is 1. 1 over 2 is 0.5. So there we've got our 6 base points. We're not doing much with them today other than show you that these 6 points are on this graph and why we chose them, to get a good idea of how to graph this. If all we had were these 6 points, we could still do a half decent job of graphing. Okay, if I only pick points over here, I would have no idea what's going on over here. So that's why we kind of break up the points so that we have equally distributed for the 2 branches. Okay, so those are your 5 base functions. Just get to know what they are, what the actual equation is, what the graph looks like. You might not memorize these yet, but you will find that when we get to a certain point in this unit, you'll need to know what they are so that you can graph any type of reciprocal function. And you'll see all sorts of other family members of this parent function, as well as the other parent functions. Okay, so for this lesson, there's no homework from the textbook. I just want you to get more familiar with the base functions. So I've got some instructions here. Basically, read through them. And you're using your function notation here, so a little bit of practice with that and noticing patterns that you're seeing when you apply. In the first question, we're graphing f of x for each of the base functions, and then graphing f of x plus 2, and then we do the same thing for the second question, but this time x minus 3. So give that a try, and that'll help us on the next lesson when we do transformations, translations specifically. Okay, so that's it for today. Have a great day. We'll see you on the next lesson.